array in Hilbert space, which means complex projective vector, projective unimodular vector, because they represent probability. So that's what we demand. Yeah. And we understood that this implies, so that let me write that statements and then I'll say what it implies. So the second postulate was observer can't measure the states directly. There is no way to access the states, and again that's why I always wanted to put this state in quote unquote, because it's not the usual sense the word state is used in classical mechanics or classical context. So here you cannot measure the state directly, but it gives you a prescription of the probability or what can you get when you measure. So what is an observable here? So observables. So observables are, so this thing is called a Hilbert space. So observables are Hermitian operators in Hilbert space. So the AC couldn't be turned on, no? The remote must be in the other room. Observables are Hermitian operators in Hilbert space. These are the objects that you can observe, but you need to present it like that. Then observable, so must be represented by something in this formalism that is a operator in Hilbert space that acts on the states and gives you a number. Okay. And this is represented as a matrix, a most convenient good morning, represented as a matrix, and a measurement of observable returns one eigenvalue, one of its eigenvalues. Okay. So there is a fourth postulate which I will talk elaborately later, that is associated with dynamics. But let's not fourth, fifth. Okay. Returns one of its eigenvalues, and a consequence of this statement is in this Hilbert space the eigenstates, of course this is known from mathematics, but it's also important to have this statement here in that we elaborated earlier. The eigenstates of this Hamiltonian, I mean we need not use the mathematics to get that, but it's useful that already that structure is automatically there in mathematics, right? Because we argued that there are these only two possibilities, and that we know as an empirical fact from these Stern-Gerlach experiments, or more possibilities if you look at some other experiment. Eigenstates of this Hamiltonian, not Hamiltonian, Hermitian, of this Hermitian operator, and the Hermitian operator forms a complete state. And there are other properties which I am not writing here. The completeness is very important, but other properties like real number, orthonormality, etc., is also there. Okay. Now there was an important consequence of this statement that comes from I will not write it as a separate postulate, that is when two operators, or let me say two observables, are involved. Let me write it there. I'm getting two. Then we learned that there is an important thing happens, which is a consequence of these postulates, that what you measure first and what you measure later, that affects a lot, and whether it affects a lot or not, that also becomes important. Like or involved, then if their operator representation commute or don't commute, these two things are totally different. So this is AB not equal to 0 and this is AB equal to 0, because we learned that they must satisfy a relation like this: delta A square delta B square must be greater than equal to AB square H cut square by 4. Okay. So because this relation has to be satisfied, then it matters a lot whether AB commutes or not. Okay. And that has some physical consequence also. To simply think in this way, that if you measure one observable, it is projected into one of its eigenstates. Now if they commute, we learn that they have the same eigenstates. So then if you measure the second observable, it's already projected into that eigenstate, it will give that corresponding eigenvalue. But that factor is not there if they are non-commuting, which means it projected into one eigenstate which has no relation with the second observable, and second observable will be now projected into its own eigenstate, which is again comes from the same, which you calculate by usually calculating the inner product of that eigenstates of where the first observable was projected into and the eigenstates of various eigenstates of the second observable. So it's simply that fact, and that leads to a very far-reaching consequence, is this uncertainty principle. Okay. So let me elaborate a little more about the statements, and then we go on to the dynamics. So the first statement, so all these statements implies, they gave us the structure that, so let me not just illustrate that. What does this mean? All these statements mean. So it means that you can express an arbitrary state, which is a complex Hilbert space, into any arbitrary basis. But let me choose a particular basis, which is this, which is the completeness. And generally for completeness, you could have chosen any arbitrary basis, but generally you choose the basis of a eigenbasis of an operator that you are measuring. Like for a Stern-Gerlach, we chose plus minus z. So this is our CA prime, and that tells you if you perform a measurement of the operator, some operator whose eigenstates are this A prime. So let's say some A prime, A prime, A prime. Measurement will project that state or collapse that state in the language of Copenhagen interpretation. Will collapse that state into that eigenstate, collapse the state psi into that eigenstate A prime with probability amplitude CA prime and probability CA prime square. Everybody is, I hope, super clear about this. And therefore, the CA prime square must satisfy the probability properties. Okay, the total must be 1. Now we also learned that about this. There are subtle things which we learned about this. That, for example, there could be an arbitrary phase factor which doesn't matter. These probability amplitudes are invariant up to an arbitrary phase factor transformation because the physical observable is probability, which is square of that. And we also know that these arbitrary phase factors either can be local or global, which means you can put an arbitrary phase factor either here or at each of these terms. It doesn't matter whether you do that, but what matters is your all other states in the experiment or whatever physical scenario you are considering must be adjusted according to that. Their interrelation matter, their specific choice that doesn't matter, and that is the main essence of the statement, that they are rays, because their direction and amplitude, none of them matters, but relative direction and amplitude matters. And then we learned about this second statement that, okay, let me illustrate this first statement once more. The important object is the expectation value, which you can express as that, as the fact that psi prime a prime a double prime psi and this is basically a diagonal object because of this. So this is nothing but delta a prime a double prime a prime, and this is psi a prime a double prime psi, which you can just write as and if you want to remind yourself about the fact that because of the a measurement is a projection, a measurement is a projection of the state into one of its eigenstate, you can alternatively rewrite it as a prime psi pa psi. Yes. What onwards? This is why? It's anyway such a small board, and top of that part of it is missing, and nobody says anything. That means probably nobody is there or nobody is watching. Okay, like that, those two, right? Okay, so this thing you can alternatively rewrite as a prime that is okay, and so everybody understands this notation, right? That what is projection operator? Why does it work? Let me check. How many students are there today? 25. Oh, such a huge absence. Don't tell me later that I don't understand stuff because you didn't pay attention or pay any effort. Okay, somebody can you tell me that did you understand this statement? Why a prime psi a prime mod square is equal to a prime psi p a prime psi? I already made this statement as a physical statement that okay, an observation is nothing but a projection, right? That you project that state into one of its eigenstate, but that statement has a mathematical representation, which is this, that I write it as a prime psi p a prime psi. So why these two statements are equivalent? Can somebody explain that? Somebody, Rishi Chaurasia, are you there? Okay, so this is a form of attendance that now I know that how much people are paying attention. Okay, very good. So now I know that why nobody understands in this class quantum mechanics. Okay, someone else. Roshan Anil, can you tell me why this is A prime psi, P A prime psi? Roshan Anil, are you around? Are you there? At least you can say yes or no. Then the next question is whether you answer this or not. That I am not even expecting right now. But you are present or not? Okay. So out of 26, how many are actually there? Somebody else? Shubhadeep Datta? Shubhadeep
Yes,
Datta,
sir.
are you there?
Yes, sir. Like if we measure a observable, then
I
we will
can't hear
get
it.
it, and when then the
I can
state
see
will.
that he's saying something, but I can't
Yes,
hear it.
when we measure a observable, then the state will collapse into an eigenstate of the operator. So
Ah,
as this psi a prime is a like eigenvalue after
I
observation,
understand that statement, but I'm saying why these two are equivalent. Can you tell me what is the mathematical form of PA prime?
a prime can be written as bra a prime into ket psi.
Sorry, PA prime is what?
Pa prime can be represented as summation of ket a prime, ket a prime,
Kate A
no,
prime
no, ket a prime into bra a prime.
into bra A prime,
Yes,
like this.
yes, ket a prime, bra a prime, then p a prime,
Then
p a prime,
T what?
t a prime.
T A prime.
Yes, after that k a double prime into ket a double prime into bra a double prime. It's the
Okay,
matrix
and
representation of the operator.
but that is just a, you are using just, but that doesn't help you to go from here to here, right? Does it? Does
No,
that help you to go from here to here?
no.
Okay, so what is the form? What is PA prime?
Pa prime is the operator that measures the momentum.
That
That measures momentum.
that measure what?
Momentum.
Oh my God. Are you even listening anything? Okay, can someone else? What the hell? I mean, is it that early? It's 8:50. What happened? I am saying you explicitly it's a projection operator, and you are saying it's momentum. Oh, I am
Is
totally
it necessary?
frustrated. I'm
What?
feeling like, what am I doing?
Is it?
Do you know that what is it now, or can you think a bit more, or someone else can tell? Where what is happening with this class? I mean, okay, how about somebody? I think let's not go through this too much. Shayantan Mandal, one of the any Shayantan Mandal of the two. Can you tell me what is that PA? Even you are not there. Okay. Ah, okay. Somebody else, anybody knows what is PA prime? We talked about projection operator. How come you don't even know? And how come you are saying it's momentum? It means you are not listening even 2 minutes
So
before
it's
what I said.
just
It's okay, but I'm saying what can I do to help this situation? Somebody
it's
maybe, yeah, Bignesha, tell me what it
yes,
is.
it's just get A and Rai without sums.
Okay, yeah. So this is a projection operator. Its job is to project on A. Okay, it's not momentum. I have not even brought even where did I? I'm talking about an abstract notion of quantum mechanics. Why do I even have momentum? There is no momentum. This is just an operator that projects you into that projects the state into one of the eigenkate of state. So that's why this quantity psi P a prime psi is nothing but psi a prime psi, which is nothing but psi a prime naught square. That's all. Okay, that is why I could write this as that. Okay. Anyways, I am surprised that after quantum mechanics exam, usually people is at a good position. They know stuff, but at least the topics that are discussed in the class. But this is really disappointing. I mean, let's just go ahead, not spend any time on this. Okay, so then we further understood about two operator business. I think it will be better for me if I don't ask many questions. Then I have to revise everything I said till date. That's not possible. Okay, then we talked about a two operator business. That operator A projects it to one of the eigengates, then operator B will project into one of B prime's eigengate. But as we discussed earlier, that if A B commute, then they will have common eigenstate, which means they will have this relation A prime, and B prime, not B prime, A prime, which means their eigenvalue may not be same, but their eigengates are at least same. Okay, so therefore, if you measure the second one, you will get back. You will project it into the same eigengate only because it's also eigengate of B. So you will get basically A prime. Here you will, the value you will get is A prime, and here the value you will get is B prime. But if they are not, okay, if they are not those kind of eigengates, then you have to express if AB is non-commuting. Then you have to express A prime in terms of B prime. Then this will be the probability amplitude of projecting it into B A prime with the and to get the value B prime. Okay. So everybody knows this much, right? So let me write this as dB prime B. And it will have its own set of rules that sum of dB prime naught square is 1. Okay. This was the meaning of this statement. Okay, that was all revision of what extensively we did in quantum mechanics in everything till before mid-sem. Okay, there is one more thing I have to revise. Two more things. One is about continuous observable, and the other thing is about dynamics. And from the dynamics, I will start continuing on something new. Okay. So all these postulates, all these 4 postulates, and it's all corollaries that I wrote down. They can be all be so. Okay. All these postulates, which goes without saying, but I'm just writing it just to remind you, because it's general postulate, can be extended to infinite dimensions or continuous variables, which is not hard to guess because all this discussion we had so far is general and abstract. That doesn't depend on the dimensionality or anything. Okay. So that we use to understand. So we made this so now comes the one more postulate. Because in the case of finite dimensional quantum mechanical problem, you can empirically or by some way or the other experiment or something, you can clearly tell that what is the dimension of the Hilbert space. Okay, and then you can know these are all the possibilities, such that spin half this case. If you send millions of electron, or maybe okay, let's say at least 1,000 of electron, you know 500 of them going there, 500 of going there. So these are all exhausted possibilities. There is no other possibilities because you have used up everything. So then you know the Hilbert space dimension is only 2. But you cannot say such thing with confidence when there are infinite dimension, right? So you have to make a postulate that these x prime, they form a complete Hilbert space. So that's a postulate. But when you make that postulate, you can calculate observables and everything, and that is consistent with that postulate. Okay? That is what is the point of this. And we learned we can play the same game here as usual. We can write it as x prime psi, and well, we can write it as summation, and then we remove the summation by an integral, and that is nothing but psi x prime. This thing is psi x prime, a function, and we have learned that we can do the same thing. So now I can put p here to write it as p. And I worked out this object is nothing but e to the power I p prime x prime. So this is the kernel of this transformation, or if you want to think in the matrix way, it is the transformation matrix that goes from one space to another space. Okay? And we also learned that only for continuous transformation, you can take a state kate to another state kate without any measurement. Okay? So you can think in terms, well, you can do it also for discrete transformation. There is nothing special about continuous, but when it is continuous, then this transformation is described by a generator, and we learned that generator is this for this particular transformation. This generator business doesn't exist for, of course, discrete transformation. It only exists because we used all this Taylor series expansion or small infinitesimal elements that you can only do for continuous transformation. And we learned that from here actually we worked out this p prime x prime for a finite transformation. So d acting on x will take you to prime plus delta x prime. And for a finite transformation, the d you need is e to the power I p prime x prime by h bar, which is basically that same kernel of this transformation. And we found from here there must be a relation between the operator itself and its generator. We did it in very generic way, and for this particular case we found that to be xpx ih bar, and we also worked out the form of the operator, which is ih bar del x, if we know that operator in the x space. And we also did it the other way, which is I can also rewrite the operator p, operator x as ih bar del p, okay? And so on. I mean, basically all these things we learned in the continuous transformation. Okay, so this is a revision of all the continuous transformation business. Okay, now I will move on to the dynamics. I'll quickly revise the dynamics and then I'll do something new. So at this point, it's a good phase to ask some questions on everything we learned till this point. Is there questions up to this? Okay, good.
Sir, I have a question.
So let's move on to the dynamics.
Sir, in the discrete case, we learned that bra x prime and kate a prime is a scalar, but in the continuous part, we are telling it as a wave function. So in the assignment, you told that a state kate can be treated as a wave function, but here we are treating a scalar as a wave function. I didn't get the point. How?
Oh no, this is also a scalar. So this is also a scalar,
Yes,
right? Isn't it? So this is a number. This is a scalar for point for the state A prime,
Yes.
this is the scalar C A prime. Right? So this is also similar. This is each point. So probability of measuring finding a particle at a particular point in space is like saying that it is collapsing that particle at that point in space, and that is associated with a state K. So the state K associated with that point x prime in space is Kate or bra. Okay? So this inner product is that number that tells you what is the probability amplitude to find the particle at location x prime. Now, if you do it for a continuous line of x prime, okay, this is the x prime line. Every point it's a real number line, and for every point there is a number psi x prime. So that's why it's a function, right? So it's also a scalar function. So this is not a function in that sense, in a real number sense, but it's still a number. Okay? It's a complex number,
Okay.
right? Is it clear to you fully? Okay, very good. And we also argued earlier that you can think all these things as a vector also, infinite dimensional vector. This x prime. These two are the exact saying everything is exactly same. It is just you are familiar with this notion of function, that's why I'm using the word function. And that is applicable here. So if you have understood this much and the dynamics, then the quantum mechanics 1 is nothing but it's more or less done for you. Rest is, of course, done in the sense rest is basically internalizing these ideas through problems. That's what will happen in the rest of that. There will be some more formalism when symmetry comes, and I don't know at this pace whether we will be able to go there, but that leads to a thing called angular momentum algebra and everything. But that's formalism. There is nothing fundamental or new principle there. The new principles are all here except dynamics. So make sure that you really internalize this, and for that it requires a lot of effort. At the way you are doing it now, it will not going to come into you. Okay? You have to really invest a lot of time at this to properly understand basic quantum mechanics compared to anything else, because as you must have realized by now, it's a very, even the properties of a single particle is very unusual and strange. That is, and you are learning Newtonian mechanics, electrodynamics in school, okay, properly, like learning it properly. Of course, now you are learning more and more sophisticated formalism of, say, doing the same thing, but that is not the case for quantum mechanics. You have never encountered like this anywhere before, and even the basic formalism is very strange and peculiar. So you have to invest a lot of time, and if you are not doing that just by listening the lecture, and in this case, as I experienced, you are not even listening the lecture, this is a huge waste of time. This whole class is a huge waste of time for you, okay, if you are not doing that, because there is no way this is going to make any sense unless you spend a lot of time thinking and talking with each other. So there are three things. You must read the book. First of all, you listen the lecture, of course, watch it. And by listen, I mean actively listen, actively participate. Then you read the book. Even that is not enough. Then you solve the problems and discuss with each other. This fourth step is very important. The third and fourth step. The first two steps are there anyways, always. You know that. You have to listen the lecture to read the book. I don't need to tell you that. But solving the problems, that is also kind of, but talk about it with each other. Unless you do that, you will not understand it, because it is strange and peculiar. The only way you know that you actually understood it, if you are able to defend this idea with against someone. So if you tell it to someone, they ask some questions, present a peculiar scenario, and you are able to defend it, then only you will understand this. And this exercise doesn't happen from textbooks. That's why people come to universities and colleges, because they get good batchmates and colleagues. People don't come to university or college. Otherwise, if you could have read the book and listened the lecture, understood everything, there is no need to come here all the way. Okay? So make use of that. Do talk to each other and try to internalize the topic. So final element of the ideas in quantum mechanics 1 In quantum mechanics 2, you will learn one more strange idea that is called entanglement, and a bit of some other things like Arnold-Bohm phase, which are very particular to quantum mechanics, but they are not novel in from here. For whatever you basic ideas are here. Now it will lead to strange consequences. That is what you will learn. And entanglement is a strange, weird idea which doesn't come from this framework. It comes from, well, you can link it to some this framework, but it requires not one particle, many particle. Everything we discussed so far is one particle physics. It can be many particle physics also, but it is general. For entanglement, you at least need two particles. So that's why it's a strange thing, and will come in quantum mechanics too. And the business of many particle and everything will come there. But this is basically all, like basically all the ideas plus time evolution is all the ideas. There are some formalism that we will learn from, which comes from symmetry, but this is not fundamentally new thing. It is basically making a very very useful for a structure out of these postulates. So time evolution we discussed in the same spirit as space translation, except the difference that time is treated as a parameter and not an operator. That's the only difference. Okay. So that tells me that I can get a psi t from a u t prime psi. So if I know a state at t, I know how this t goes to t prime without any measurement, just evolution. Okay. So that's very important, just like this translation. And we also constructed the form of this operator. When t and t prime are infinitesimally close, they are only delta t gapped, then the form of this operator is and then if it is finite, we found it minus IH delta t by h bar, where delta t is, so delta t is infinitesimal, and this capital delta t is finite. Okay? And then we also found a differential form for this, which is IH bar d psi dt if h psi, which is the famous Schrodinger equation. And we said that this H is the generator of the translation, and H is the H is a energy operator. Okay? So we identified that with Hamiltonian from our classical mechanics experience. So today I will make that connection a little stronger. I will tell you why it makes sense to call it that. But let's just proceed from here without really making a judgment on what is H, what exactly, why it is energy and so on. But let's just accept the fact that H is Hamiltonian, and see that what all you need in order to calculate things, in order to understand that how can you calculate the time evolution, how can you calculate the expectation value of time evolution. And then we'll come back and discuss again that why do I identify that with energy or Hamiltonian. Okay. So now the problem of, we also discussed that the problem of time evolution boils down to knowing the eigenspectrum of H. H, eigenvalue and eigenvector. That's the meaning of eigenspectrum. Okay. So H J is EJ J. Okay. That's what you need to know. And once you know, so once you solve that, so this is actually one of the most celebrated equations, and everywhere you will find this. Oh, you have to. This is a static Schrodinger equation which you have to solve in all these particle in a box, all these problems you might have done in previous course. And that once you solve that, you can easily calculate any dynamics. Okay? So how is that? Of course, it's easy to see that psi t is u. Let me write it just as u without all this t and t prime. So here I write it as j prime psi t and u is e to the power minus I h delta t by h bar j prime right, and that is nothing but this is nothing but let me not write psi t, let me write psi 0. By taking the t as 0 and t prime as some t, okay? Because I want to connect it with something static. So I call it Cj0. And we identified this pictorially, this object as, so psi 0, you can think it as like every j. So every j prime, you can write it as 1, 2, 2, some infinity, whatever. So this is my j prime. Okay? And each of them has a Cj associated with them. Okay? When I express an arbitrary psi in terms of this, which is this? This is the Cj. This is the Cj. This is the Cj0. Now, what happens when dynamics? I apply dynamics. So each of them is multiplied by a unit circle, unit phasor. Okay. And with time, they move at defined speed, and that speed is given by this Cj prime. If it is large, it moves faster. If it is small, it moves slower. And what is a time? If you are asked that what is the time evolution up to time t, then at time t you freeze that evolution. That's where you take a snapshot, and this particular set will give you what is the time evolution at that. That will allow you to calculate this particular superposition with those phasors. Will allow you to calculate the psi t. This is a pictorial way of remembering this. You don't need to think it like that, but I find it useful to remember when you think like that. Okay. So then you can go on and calculate anything you want. You can calculate objects like AT. So let me go a little details here, because since it was the last topic before medicine, it's not exactly a revision. Well, it's a revision, but so now you can calculate anything like, let's say you want to calculate some B expectation value as a function of time. So then you have to do, let's say you want to do it for states not alpha, psi t, B, psi t, okay? B at time t. So then you can write simply as psi u dagger B u psi. This is psi 0. And that is nothing but I just use this formula twice, okay? And this is Cj prime, Cj double prime, e to the power I, Ej minus Ej double prime, t by h bar times j prime b j double prime. Okay? So this thing is sometimes written as omega. So omega is omega jj prime so you write this as Cj prime, Cj double prime, e to the power I omega j prime j double prime times t b j prime j double prime. Just this matrix element. Okay, just a shorthand of this equation and nothing else. Now, just to note that one thing, that if this psi t is already an eigenstate of B, of this B operator, then there is no time evolution. Why? Because this thing will project in exactly that, and this will cancel with each other. Okay? So then you will get no dynamics. That is what we discussed earlier. And those things are called stationary states. So from here we learned that eigenstates are stationary state, which is also apparent from here, right? Because we saw that each of the eigenstates of this E operator, eigenstates of H. So this is important, that when B has the same eigenstate, that means B and H have commuted. So it is important to note that, and that is easy to see from here, because what we have seen that this each state just is multiplied by a phase factor. Just because the state that you are evaluating is not a eigenstate of H, is a sum of those phase factors. It's a sum of those linear combination with those phase factors. But if you are measuring actually an eigenstate, then it will not have anything. It will not be a sum of anything. It will be just that state with the phase factor. And we know the phase factor doesn't show up in probability, and that's why the state is not evolving with time. So the statement is, if you are measuring, if you are looking at any state that is eigenstate of the Hamiltonian or the generator of time translation, then that doesn't evolve, and that's not a new statement. It means you have already projected it there, and there is no time evolution. And the only thing happens is that it gives a phase factor, and that phase doesn't matter because all the measurables are phase independent. Sorry? Yeah, because if I have a quantity, what is a probability amplitude? It is Ca, right? So if I multiply it with a phase factor, e to the power I alpha Ca, that will not matter because probability is square of that. Okay, so that is the meaning of that statement. Okay, so this is all that we discussed earlier. So now what I will tell, so I will give you two different ways of thinking about this time evolution and make it and give it some connection with classical mechanics. Okay. So this is, somebody asked me that question, that the question was in the context of time space translation. I think Sresha, what is his name? Yeah, anyway, I think anyway, so the question was that instead of thinking of a translation of an object or a physical observable, what if I think it as a translation of coordinate frame, which is also perfectly fine. Any transformation, the rotation or anything, you can think as a transformation of coordinate frame or the physical object. And you learn that in classical mechanics, there are two types of transformation called active and passive. In quantum mechanics, you can totally formulate them and go from one space to another. It is, I didn't discuss it in the class, but it is discussed in somewhere in Shankar. But what I'll do, I will do these two type of passive or active transformation in a different sense, because time is special, as you know, that because time is not observable. We'll discuss these two type of transformation in this in context of time, and that will give two different formalism and make a very interesting connection with classical mechanics. Okay? So let's do that. I hope everything is fine up to this revision. Till now, I have not done anything new in the class. It's all pre-midsem revision. I hope everybody is clear up to that, and if not, this is a good point to ask. Okay. So now let's go to a picture. So I am not talking about basic. Well, this is also kind of basic. Well, not exactly. It's a formalism. So Heisenberg picture. So where does it come from? It comes from the fact that you can think a transformation, a time translation, either as a property of a state or either as an operation on a state or as an operation of operator. It doesn't matter, because end of the day you are not measuring a state, you are measuring an observable, and what you are actually measuring is the expectation value. What is actually relevant to talk about in the context of experiment is the expectation value. So this is an alternate way to view time translation. So let me call the usual way Schrodinger way. So this is the Schrodinger picture where you translate the state. This is the Schrodinger picture, and you learned that according to this picture, psi st IHS, I'm writing everything that I wrote before, but except I'm putting this subscript s just to remind you this is Schrodinger. Later I will use Heisenberg, that's why I will keep another notation. It's exactly the same. But what is significant is this quantity. So let's say I want to look at an observable, and but experiment in the context of real world or experiment matters is this object. Everything else is a construction that leads to this object. Okay? So this object is nothing but so let me define a new operator. So now the idea is simple. The idea is, since this is the only thing matters, instead of saying that the state is transformed, I will say the operator is transformed. That is it, right? Very simple idea. So that, and that has a very far-reaching consequence. So I'll define an operator. So I'm not saying now anymore that the state is transformed. I want to say the operator is transformed, and that is given by this similarity transformation. I have taken this whole object and written here. Okay. So this I call as Heisenberg operator. And now my psi h doesn't evolve because the time evolution is taken away. And this is nothing but my psi z. Okay, this is the definition. So now I can rewrite this as this thing as because psi h is the one which doesn't evolve, and aht is basically contains all the time evolution. So now I can write, so this is the infinitesimal version of this. So now I can write an infinitesimal version of this. So I have to take a derivative of this operator. Okay. And this is the exercise which I want you to do, but I'll show you, it's just 3-line exercise. Okay. So this is the parameter. So you have to take derivative with respect to that, and that will give you I by h bar. Actually, there is no exercise. I have solved it. AH0 minus A0H. Maybe just do this one line. Take derivative. This is your homework. Given your current state, I am afraid to give you anything more. Okay. So this, so therefore that tells me. So this is nothing but a commutator, right? HA minus AH. So this is okay. So starting from here, convince yourself that you get this. This is just 2 lines of algebra. Okay. Now, why this simple trivial exercise is so interesting and so insightful? Because this gives you a simple connection with classical mechanics. Because you know, in classical mechanics, so let me write it here. So let me give it a name also. This is called Heisenberg equation of motion, which is the equation of motion of the observable. Okay? And this is our you can also put T here. Schrodinger equation of motion of a quantum state, and this is for that of a operator. Now this is going to be more useful to us because more useful to us in the context of experiment and connecting it with real world, because the physical observables are corresponds to classical variables, right? So in classical mechanics, the states are observable are the same thing, because what you can measure is the state, the position, momentum, or whatever other attributes. In quantum mechanics, the states and observable are not the same thing, because what you can observe is not the state. The state is the psi, what gives you a prescription of what you can measure. So if the physical observables if you want to talk about them, the classical physical observable, if you want to talk about its quantum mechanical counterpart, then you should talk in terms of these operators. Okay, these operators are observable. So that's why it's very useful to have a equation of motion that is not of the state but of the observables. Okay, so that's why it's particularly useful. Now you have seen this before in classical mechanics. You have seen this object called Poisson bracket. Okay. This is the same thing as that. So let me, for the sake of generality, I drop this part. This comes if there is explicit time dependence on the observable. So if your A is function of Qt, Pt and T itself, then you get that extra del A del T. But if I just remove that part just to make that connection, you can also bring that part here. I'll come to that later. But since now we are talking about time independent of operators, so that's why I'm dropping that. In quantum mechanics too, we will talk about them also. So if I want to make a connection, so what is this object? This object is nothing but del A del Qi. Poisson bracket is this, right? This is this object. Okay? So now we obtained a connection between this classical dynamics and quantum dynamics, and this gives us another motivation. So notice that in all this discussion, I never need to identify what is H. H is some operator which is generator of time translation. But now this correspondence tells us you can call it the Hamiltonian, because in classical mechanics, the object which gives you this sort of equation of motion is the Hamiltonian. And you can say that you can take a classical observable, and classical observable A is some observable, and its dynamics is given by this, and you can simply go to quantum by replacing this by this, by replacing this by quantum by commutator divided by 1 I by h bar, I h bar. And one more thing, of course, you have to do, you have to put hat on everything. So A becomes A hat, H becomes H hat, because observables are not numbers in quantum mechanics, they are operators. Okay, so this is an operator equation, and this is an equation of a function. So think about this point, and that's where I'll stop for today. And the next class I'll make a more elaborate connection with classical mechanics and quantum mechanics. Okay, so that's all for today. Questions at this point? Okay, good. It was all mostly revision, but near the end we talked about this Heisenberg picture, and because we wanted to have a equation of motion or a dynamical form which is in terms of observables or in terms of objects that you measure in classical mechanics. In state, state is not a measurable quantity. State is a prescription. That's why I want to shift from dynamics of state to dynamics of operator. That's the picture. Okay, that's all. You can stop the